Hey guys, welcome back to another video. Today we're going to be doing another UKMT question using the mind map method. So this is the question. Tiny pattern shows two types of tiles, regular hexagons and equilateral triangles, with the length of each side of the equilateral triangles equal to half the length of each side of the hexagons. A large number of tiles is used to cover the floor. Which of the following is closest to the fraction of the floor that is shaded black? So if we make a mind map for this, you have a pattern of hexagons and equilateral triangles. So these are regular too. So each side of the equilateral triangle and the side of the hexagon, so that is basically half of that side, and then a large number is used to cover the floor. So which of the following is closest to the fraction of floor that is, so all of these, so these are a large number, and then which of these are fraction shaded black. Okay, so that's our mind map. First we would want to find the ratio of the triangles to the hexagon, so we know the fraction of which the floor that is shaded black, because whatever's being shaded black is basically the triangles. So you want to find the ratio of the triangle to the hexagon in this pattern. So we know that the length of the triangle, which is equilateral, is half of the length of a hexagon. So we'll just say that the lengths of this equilateral triangle is 1. Of the equilateral triangles are 1, and then the lengths of the hexagon, which is a regular, so which means all sides are the same, is 2, because that means that 2 triangles can fit on one side of the hexagon. So to find the areas first, we want to find the area of the hexagon first. So we can divide the hexagon into shapes. So we can draw a line here from the vertices, and we can here. So we've got basically two squares and 4 right angle triangles. We know these are right angle triangles because if we know this is a square, so these are 90. These angles are 90. And if these angles are 90, then these angles are 90. And we know these are congruent because they have the same hypotenuse and right angle, and they also share a side. So these are congruent on RHS. So we'd probably want to find out the height of the triangles, so then you can find the area of these small triangles and then the big ones. So we know the hypotenuse of the right angle triangle is 2, so you'd want to find the height, and we know that this angle is 90. So we'd want to find the other angles of the triangle, so we can use our sine cos tan rule. So if we know this is okay, so we can do that. So we know that all the angles in a regular hexagon add up to 720 degrees, and because there are 6 angles in a hexagon, you just divide that by 6 to get 120 degrees for each angle. So this is 120 degrees, this is 120 degrees, 120, 100, 120, 120, and 120. And we know that in this triangle, in the squares, these are 90 degrees. The interior angles are 90 degrees, so that means these angles should be 30. So that's 30. So if we know these angles are 30, then we know that these angles have to be 60. And then, therefore, proving that these are congruent because they all have the same angles. Yeah, so that's 60. We've got 60 now. So now we can use our sine cos tan rule to find our height of our triangle. So we can use sine. We can use the sine rule, which is basically sine x equals opposite over hypotenuse. But in this case, we can use sine 60 to get our opposite over 2. In this case, we will do sine 60 here, and then its opposite, which is this side, and then the hypotenuse of here, which is 2. So we have sine 60, which equals O over 2, and then rearranging it, you have sine 60 times 2 equals O. So sine 60 from our previous video, I remember that sine 60 is root 3 times 2, which equals O. So root 3 over 2 times 2 is just double of that, so that's just root 3. So O equals root 3. So now we know O equals root 3. The height is root 3. That's root 3. That's root 3, and that's root 3. So you have all these root 3's. So now we've got our hypotenuse and we have our opposite. To find the base of this triangle, which we would need to find the area of the triangle, we can use Pythagoras Theorem. So if we just redraw our triangle, so we can clear it, we can see what we have. So basically we have our root 3, which you just found out, and we have our hypotenuse, which is given. And this is 90. So we can use Pythagoras Theorem because it's a right angle triangle. So we just do 2 squared minus root 3 squared, which is so x basically, x squared. So that's 4 minus, so root 3 times root 3 is just 3, which equals 1 squared. So basically 1. So x equals 1. So on here we now have, so both of these, so the side that all the triangles share is 1. So we can do 1 here and 1 here. We have 1 now for these sides. Now we can use our base times height over 2 to find the area of the triangles. So we have base, so we have our base, which if we look at it as a whole triangle now, if we look at it as a whole triangle now, to make it easier for ourselves, we can do, we have our base, we have our height, which is 1, and we know that our base is basically root 3 plus root 3, which we have as 2 root 3. So base times height, so we have our 2 root 3 plus times 1 over 2, which is basically just 2 root 3 over 2, which is just root 3. So that's obviously for one big triangle. So then for both triangles that would just be 2 root 3. So the areas, so for the areas of the two triangles we have 2 root 3. Now, and then we can also find out the area of the big rectangle in the middle, because we know that the side here is 2, so we just do 2. So we'll just do 2 times 2 root 3. So 2 root 3 is basically root 3 here plus root 3 here to get our height. So 2 times 2 root 3, which equals 4 root 3. So we have our 2 root 3, and we have our 2 root 3, and we have our 4 root 3. So then below we can do 2 root 3 plus 4 root 3, which equals 6 root 3. So 6 root 3 is the area of our hexagon, of one hexagon. Now we know so we can, got that, so we can say this whole thing, so 6 root 3, I don't know how to, yeah, so 6 root 3 is our whole thing, and then we can find out the area of our triangle here. So because we can split it in half, so we use Pythagoras Theorem, so we have 0.5 here. So we have 1 squared minus 0.5 squared, so if we go down, drawing it again, we have 1 and then 1, and then halving this, you have 0.5. So 1 squared minus 0.5 squared, so 0.5 squared is just 0.25, so you basically get 3/4. So 1 minus 0.25 is 0.75, which is also 3/4. Square root 3/4, so that basically equals square root of 3, and then square root of 4 is 2, so square root 3 over 2. So that is our height. So this is our height here. So root 3 over 2. That's our height. And now we want to find the area. So our whole base is 1. So 1 times root 3 over 2 over 2. So basically root 3 over 2 divided by 2, which is root 3 over 2, which is root 3. So basically it says, as you're saying, a half divided by 2 times...
Yeah, half of root 3 over 2.
Okay, so it's half of root 3 over 2, which is a quarter.
Again, sorry, a better way is half of the half of root 3.
It's half of the root 3, which is basically a quarter of root 3. So the answer to this is root 3, so a quarter of root 3. So that's our area for our triangle. Our whole triangle. So now if we compare both areas now, so we have our root 3 over 4 to our 6 root 3. So to fully compare it with the same bases, we can multiply both sides by 4. So you basically have root 3 equals 24 root 3, and then cancelling both sides out, you have 1 to 24. So now we know that the area of the hexagon, so area of H, and the area of the T. So we know that the area of the hexagon is 24 times bigger than the area of the triangle. So now we know the ratios of both the hexagon and the triangle. We need to refer back to the question where it says, which of the following is closer to the fraction of the floor that is shaded black? So from the beginning we know that this was a pattern. We don't know, because it's a pattern which has a large number of tiles, it's an infinite plane, so we can't count how many triangles there are in this floor, and we can't count how many triangles are on this floor. So we try and find a repeated pattern which is repeated along the whole floor. So this relates back to tessellations. So this is a concept of tessellations. So we have our we have our hexagon, which is here. So if we draw a hexagon, we have our hexagon here, and then we have our 2 triangles here. So obviously these triangles take half of the side and whatever. So this is a whole shape that is repeated along the whole. So we have another one of that here and here, which fits together nicely with no space in it. So we have that. So we know that the hexagon is 24. So if we just keep the unit as 24 here. So the hexagon is 24. And we know that the ratio to that. So if the hexagon is 24, then the triangle is 1. And then we know this triangle is 1 too, because they're equilateral and they're the same. So in this whole repeated shape, so if we draw the shape out, so in this shape, so in this big shape, we have 26 shapes in total. So the area of the shape is 26, and out of 26, the triangle is 1. So the one triangle is 1 out of 26, but we have 2 triangles here. So the triangles out of this whole shape are 2 out of 26 square units or whatever. And then simplifying that to get 1 out of 13. So the triangles is 1 square unit out of the 26 square units here. So this is our answer, which is D. Because it's an infinite number of patterns and hexagons and triangles, we can find one repeated pattern, and then we found the ratio for that. Thank you guys for watching our video. Please make sure to like, comment, subscribe, and we'll see you in next time's one. Bye.